Thank you, everybody, for coming to Manuals Are for Suckers. I'm Jason Adaska. I work at a law firm, Holland & Hart, working on essentially automation tools for the legal practice. It's a slightly non-traditional place for software development, but my hope is that some of the things that we're doing, though, are slightly idiosyncratic to this domain, have analogs that would be useful in other places. Okay. So the basic outline for the talk, I'm going to start out with kind of a squishy part, just giving you some kind of high-level overview of the motivation behind the problem we're trying to solve. Talk a little bit about arrows for those that are not familiar with them, just really briefly, and how we're going to use them, and then we'll actually look at some examples that kind of come from the work that we're doing. Okay. So, as I said, I'm working in a law firm, and there are certain things that you experience when you're a software developer working in a law firm, certain universal truths that you learn that otherwise you wouldn't necessarily come across. And one of the ones that I've run across that was sort of important for the work I'm doing is that lawyers like to read stuff. It's what they spend like essentially 3 years doing is like reading stuff and then arguing about it and then reading more stuff. So that would be neither here nor there if there wasn't an implication for the kind of work that you do when you're kind of developing software, which is they kind of expect you to oblige them. So if you go and generate some new feature for some automation and say, hey, I've got this great feature, this is going to make your job a lot easier. Before, you had either your secretary or you had some junior attorney that was drafting some part of the application, some a patent application. All that we can kind of do automated. All you have to do is send an email to this email bot and it'll fill that stuff in. They say, oh, that's great, you've got this new feature. Where's the manual? Where in our gigantic document repository can I go to tell me how to use this? Well, I just did it like an hour ago and just uploaded it. You can use it now, but there's not any manual for it. So I got that question enough times that I started thinking about the way in which we were working. So in our firm, we have a very small group. We work very closely with the attorneys and the paralegals and whatnot. And people have seen these kind of iterative environments, but there were certain pieces of it that didn't become real to me as like having some kind of technical problem associated with it until I started, basically coming across these same kind of questions. So obviously, coders, they like to code, right? That's a part of the iterative process where you're kind of adding your artistic 2 cents that feels like you're kind of creating something. Testing and deploying, that's usually not very fun, but there's tools that kind of make that easy, right? They kind of flow out from the source code. I can use quick check and it makes it very easy to have the tests kind of go automatic. Deployment as well, there's kind of tools that make it where, though those aren't fun activities, they're not really activities I have to spend a lot of time doing. So what about like using? So using, the first thing, the obvious thing to realize is that if you're a developer, right, the person who's often going to be using whatever it is you built is not you, right? Somebody else is going to be doing the using. So it's an obvious thing, but there's some implications. One of those being that whoever is going to be using it needs to actually know how to use the feature, right? And they're looking for manuals or training or at the very least some knowledge that a new feature is available. So I started thinking, I understand why people are kind of asking for manuals. I don't want to write one. It seems like a really hard to maintain thing. Every time I write a new feature, then I've got to go to the repository and think up some documentation to make and kind of publish that as well. So the question was, is there any way for me to kind of automate this process as well? So the kind of just so story I started telling myself was, what if the program itself could describe its functionality? Right, what if you had a situation where I take my Haskell file, I add some new feature to it, I compile that and I deploy it to Mr. Computer. An attorney comes by and says, hey, Mr. Computer, what sort of things can you do for me? And the computer not only can execute that feature, but it sort of knows semantically what that involves. And can kind of communicate that. Now, there's lots of, you can imagine very like tortured ways of being able to implement something like this. We have a small team, and I was essentially thinking of what are abstractions that we could use, whereas we're building a certain new feature, it makes it easy to kind of add something like this, this kind of capability, sort of take new features not have to actually write any, duplicate any work or write any other sort of description of it, not a big man file or something like that, but actually just write the source code and have an ability for the program to kind of reason about the new feature, kind of flow automatically from it. So the abstraction that we found to be useful were arrows. So arrows, in sort of very brief detail, are effectful computations where you have inputs and you have outputs. So there's a lot of basic examples, pure functions and basically arrows, right? We can add a monad for some effect. So a brief history of where arrows came from. Oddly enough, arrows were introduced by John Hughes in a 2000 paper, generalizing monads to arrows, and he had kind of a grand vision about essentially a different kind of abstraction that would be more general than monads, and the idea of people be building libraries based on arrows, and then there'd be tools that would make it easy to be able to pull together kind of meta libraries. So one could argue whether or not that's been successful. Our interest, and kind of my personal interest in it, came more from the comments that he made about this library after the fact, which was, arrows, as it turned out, have been very useful in kind of abstractions for domains where you care about processes, right? Where what you're trying to kind of model and represent are kind of process type abstractions. So people use them for FRP. So the thought was, hey, that sounds a lot like the things that we're building, the automation pieces that we're building for the attorneys. I mean, essentially what we're doing is we're replacing work that was previously done by attorneys themselves or by legal secretaries or whatnot. So the way that people work and sort of are trained is, okay, you get a certain piece of document in, you do X, Y, and Z, you fill this thing here. So there's kind of natural ways to train people to do those tasks that have kind of a process-like flavor to it. So why not kind of use that same idea when describing automation? Okay, so in slightly more detail, the things that you can do with arrows, and this is, there's a couple of different relevant type classes that come from control.arrow, the Haskell library. Arrow itself, has essentially two operations. It has lift and it has parallel. Composition comes because it has to be in category type class as well. But essentially, so lift just lets you take a pure function. It's like return for a monad. Composition lets you, plug two things together in the way that you kind of logically expect. Parallel lets you sort of join two independent kind of computations into one thing on the tuple. Now, for a lot of the work that we want to do, there's also a notion of kind of branching, and arrow choice kind of gives you that extra flexibility. So you can split things out, you can fan things in. And the diagrams at the right give you some sense of what that looks like. Okay. So what are free arrows? Now, this is obviously a very deep subject, and it is very possible I will offend the category theory gods at some point during this talk. So I'll qualify by the way that we're using free arrows, which is the following way. Free arrows are things like free monads that you can both put together. You can compose just like you would do normal, but it's also possible you can kind of pull them back apart. And you usually pull them back apart for the purpose of kind of putting them together with new functionality, kind of augmenting them with new functionality. So we talk about free arrow, not free as in freedom, not free as in beer, free as in free monad. So this particular aspect is kind of what we're going to be drawing on to sort of represent our code in a way that has all the pieces there, has all the benefits of type checking, but lets us kind of pull it apart and reason about it in different ways. Okay. So in particular, the implementation, if you go to the GitHub repository, there's kind of a stack code example that has this and a couple of other files. So a semantic arrow class, something that's used for some of the other examples. So you're welcome to kind of browse this, but the basic kind of just straightforward implementation that we're using is essentially just a generalized algebraic data type. You'll notice that it has essentially exactly the different functions that you saw in arrow and arrow choice type classes. Here with sort of plain text constructors, so, your pure, your effect, your sequence, your parallel, your split, your fan in. The one addition is this kind of semantic annotation. Now, you could kind of build that into the effect. But for sort of syntax reasons, it's nicer for us to be able to kind of augment the, an arrow with some kind of semantic annotation. And you'll see that in the code in just a minute. Okay, so what's kind of the motivating example? So this is a very kind of the hello world version of the kind of stuff that we're doing. We have an email bot, and email bot essentially does things that people were previously doing in a lot of context. And so things people were previously doing looked like the following. Somebody sends an email. They used to maybe send it to, to Joe, attorney, and it would have some kind of attachments associated with it, with information, and maybe some information in the actual blocks of the text. To make this extremely simple, imagine that you have somebody that just wants to fill in a form. It's a very simple form. It's got a PDF, that set of attachments, it needs to include a PDF. It also has an application number, and all you want this thing to do is take that application number, open up that PDF, fill in that form, and return it. It's the most basic thing possible. Okay, so how would you sort of put together some function in an arrow-like syntax that does this? Well, there's a couple of submodules, right, or subfunctions. Get application number. So here we're, for concreteness, I'm picking a particular monad stack, or monad transformer stack. So you have your accept, you have your reader, you've got an email data object that's underneath, and all sits on top of I/O. And when you want to get the application number, what are you going to do? You're going to grab the email, look at the body of the email, and you're going to try to get the application number. Now, it may fail. You may not have, the parser may not be able to find it, maybe the wrong form, etc. So there's, you're going to try to get the application number. And if you can, you're just going to return, the text associated with that guy. Get first PDF is going to take the email. Instead of looking at the body, it's going to it's going to look at the set of attachments. So you're going to try to, filter out all the ones that are PDFs, and then you're going to try to get the first one, and that's the one you're going to use. So fill legal form essentially just does those two things in parallel. So that's why you have your sort of parallel between those two guys. You're going to get the PDF, you're going to get the application, you're going to take the outputs of those two things, and you're going to assert into the PDF. So we wrap all those things. As you can see, we kind of annotate that with kind of natural language descriptions, right? The exact kind of descriptions that maybe you would put in a comment, or if you were describing the process to a user, what it's doing under the hood, you put that kind of detail in the annotations. And then the action itself, you say, all right, this whole thing is going to fill legal form. Okay, so we can take a step back for a second. The thing that I was interested in was being able to sort of write idiosyncratic versions of this and make changes to them, and then have a lot of additional functionality flow from that. So if I want to do other kind of fancy things, like reason about this structure or represent this structure in different ways, I don't want to have to go back in here and change the code around. I want to be able to use exactly this, but have other processes that can kind of grab this structure, pull it apart, put it back together in different ways, and create different representations for it. So everything else you'll see, this is sort of this action guide is your input for everything else that kind of follows. Okay. So what's the basic thing you can do with this? Well, the absolutely most uninteresting thing you can do is you wrap these things in kind of semantic content. You've got this free arrow, so you're not actually binding the pieces together in a way that you can't unbind. The most uninteresting thing you could do is just essentially turn this into a regular Cleasley arrow. So run A does that. Right? That you haven't really lost anything in terms of what at the end of the day you need to do, which is freaking execute this thing. So main does that. Here's a simple example. Again, if you go to the GitHub repository, this is just the main function, main.hs. So all it does is it takes that takes your action, unwraps it using that run A, then runs the Cleasley, and then does the whole monad stack transformer on top of that. Okay, so let's actually do something slightly more interesting. So now we're getting towards the the kind of things that you would do with a free monad, which is I want to inject some additional kind of functionality into it. And if I just ran it, you can imagine if I just switched from having my semantic arrows to just a normal Cleasley arrow in the original code base, you'd get that same kind of functionality you saw on the previous slide. But now I want to say, you know what, I didn't build in logging initially, but I'd like to do some logging now. Maybe I want to have some representation that I'm going to send back after it actually runs to let people know, hey, this is exactly what happened. And maybe that might be relevant if there's branching or whatnot. So, there's a lot of different cases for this guy. I only put the interesting one, which is the one with the semantic annotation. And essentially what we're going to do is we're going to take that kind of semantic arrow, and we're going to take a function, and this is going to be sort of our reporting function, something that's going to be able to take one of our blocks, and our blocks are nested, and be able to turn that into a report of various sorts. So we wrap all those report elements in a state T, and basically it's spitting out another Cleasley arrow. I'm not wrapping the sort of the B to state T guy in Cleasley, but you can sort of think of it that way. So you take in your semantic arrow, you're going to spit out a Cleasley arrow, but one with a state T that's kind of tracking your, as you kind of go through the different nested layers of kind of functionality, it's going to be able to report that out. So you get a log file, all it's doing is the obvious thing, right? It's taking the semantics, it's sort of running this function, it's telling you, okay, what kind of output text do I want to have for my log before the function, at the beginning of the part when the function runs, and at the end, when that kind of block of code runs. And then I'm storing this in this kind of nested list zipper, which is something that lets us keep track of the sequence, but also hierarchy. So fair enough, you can go ahead and run that. And again, this is main one. And you get exactly what you'd expect. So now we've actually run the function, we didn't change anything, we didn't add state T to the kind of original definition for that action, but we've kind of injected it, and now we get to run this thing where we've got fill legal form, enter PDF, et cetera, all those different pieces in sort of a hierarchical form. Okay, so we've done two versions that are both kind of running that action. One of the things I was interested in was not just, how can I kind of run this thing in different ways, maybe augmenting it with different kind of behavior, but just what could we do to be able to allow the program to kind of reason about it, right? Not to run it, but to be able to kind of look at it and describe what does the process do in a different way, without just sort of having it output some things with certain side effects. So there's a natural way that sort of people, especially those who are not kind of technical, think about kind of process flows, and that's in terms of these kind of flow charts. So the thought was, well, I'd like to be able to have that kind of semantic description of what the process is without having to go in and hard code that into the process itself, or even worse, have to generate some Visio diagram on the fly, after the fact, right? That has to be updated, et cetera. So the thought was, all right, well, what if I just took that, this kind of semantic arrow that I can pull apart, and use the fact that I can kind of pull it apart to essentially generate a graph structure. So that's what this guy is doing. Again, is there a question? Again, the most interesting pieces are kind of shown here. A lot of it is just kind of recursive down. But you have your base cases where you're actually getting your pure effect thing, and then your kind of semantic tagging is essentially clustering. Has clusters. So I'm using GraphViz to do the graph layout, and that particular choice is kind of neither here nor there. You could imagine doing similar things with, spitting out some stuff to some JavaScript library or whatnot that could render this.
Can I ask the question?
Yeah. Maybe.
How is this different from just using your free monad or just doing this via free? What extra benefit does using the arrow give you? And I apologize because maybe I'm just not getting it.
So you get ins and outs. That's one of the pieces, right? So you've got an input and you've got an output. And we're doing something where, here we're not actually spitting out even, and this doesn't have anything to do with monad versus non-monad, but you're getting something that's not even an arrow at the end, right? I'm unpacking it, and then I'm not packing it back together into an arrow that has some different effect, a monad that has a different. I'm actually unpacking it to like a graph, right? A static graph description. So I mean, I guess the arrows versus monads essentially give you your inputs versus outputs, but we're also doing some things that are maybe even kind of coloring outside the lines lines a bit in terms of just free arrows.
One more question, actually.
Yeah.
Can you pull the microphone a little bit closer to you?
I actually don't know. I'm not even wearing it.
The one on the desk.
This guy?
Yeah.
Yeah. Thank you.
Might be a little bit better.
Okay. So has anybody heard the first part of this talk? We're getting to the good part now. Okay. Thanks. Is that better? Excellent. Alrighty. So if you do this, if you actually just run main2 is what this guy is, then this is what you get, right? So, again, we just sort of wrote code in an arrow syntax similar to how you'd imagine writing it, and you get a relatively nice kind of natural language and visual description of what the process has. Right? I mean, you're filling a legal form, you've got two independent routes, you've got to find the application number, you've got to find the PDF, those themselves have kind of nested pieces, and then you put that stuff together. So when I was initially kind of thinking through this is what I had thought was kind of the end game, right? I want some representation that I could give to that's kind of generated for attorneys or whoever it is that's using these different automations that kind of lets them understand what's going on in a way that's a lot more straightforward than if I had to show them code or showed them some haddock documentation or something like that. What I discovered is that there's people that kind of use tools in slightly different ways. There's some people who will be more, if there's a new feature, they're going to be more conservative. Right? They're going to say, I need to actually understand what this thing is going to do before I even try it. So I could go and say, hey, we got a new feature that'll help you fill out legal form X. And they say, hey, great, where's the manual so I can understand exactly what it's doing before I try it. This kind of solves the problem in some sense for those people. Those other people who are, and this is maybe more of a younger generation, they're just like, hey, feature X, I'm going to try it, right? I'm not going to look at the manual until I try it and something breaks. So, I mean, obviously it could break and it could, spit them back there, but in some sense that's a more efficient way of operating. And is there anything that we can kind of do here that might make that other mode of operation a little bit easier? And what occurred to me is that there's sort of an analog that shows up in kind of did you mean type evaluation for Google. So, now, I mean, it's funny, like I had this in my mind and I was, preparing some slides for this and I was like, I'm just going to like type in some stuff. Obviously that's not what Google gives you, but they don't even have did you mean anymore. They've actually, they are so certain now that they know what you mean. They don't even ask you, did you mean this? They just say, oh yeah, you're actually looking for, whatever it is instead. There's something that kind of amuses me, like working in, automation where we're sort of pulling people away because you kind of don't trust them to do as good of a job as a computer does, that Google's kind of doing that for us too. It doesn't even trust you to kind of know what you're searching for anymore. So anyway, so the thought was, this kind of did you mean idea is that I do a search and I don't quite do it correctly, right? Maybe I misspell something, maybe I don't really know what the terms are, but it knows all the different things that can be searched for and what are common and what kind of makes sense. And it says, hey, what you asked me to search for doesn't seem to make sense, but I think I know what does make sense. So the question, was, could you do something similar, right? So instead of having, they run a feature and it doesn't work and it throws some exception and says, hey, go read the manual because you're doing something, you didn't include the right attachment or you didn't format things correctly. What if I could kind of give them information back that's actionable, right? That says, you didn't actually mean, you asked me to fill legal form 1, but it actually looks like you gave me all the information to fill legal form 2. Now, how would we actually get that to work, right? So just sort of a little more kind of concrete context here. So, imagine, instead of just having fill legal form 1, we have fill legal form 1, 2, and 3. And somebody asks, hey, I'd like you to fill legal form 1. What they actually meant was fill legal form 2. Things like this, actually, I can tell you happen all the time for kind of the tools we're building. So, how would you go about figuring out whether the thing that they asked for fit some other route? And here's a poor man's solution. So imagine that, all these things are running in except T. So if, it is looking for a certain attachment or trying to parse something out and doesn't find it, it'll throw an exception. And you can imagine, okay, I'm going to re-instrument my code. I want to actually track all the different errors that it gives, all the different possible errors that it could give. But that would require me to kind of go back in and sort of change the code, which I told you I wasn't going to do. I'd like to still take that same process that I described before, which is just running an except T, and I'd kind of change it so that now instead of just stopping at the first exception, if possible, I'd like it to kind of like look through other branches. I mean, obviously causality is going to make it impossible for me to like look at certain exceptions that are farther downstream. But if you have parallel processes, which we do, right? We have an attached PDF, and we have looking for the attachments and then looking for something in the body. Those things can kind of run independently. They both might throw exceptions. If you were going to do it just naturally, just doing a run completely error, it would hit one of those things first and it would throw an exception. We wouldn't get to see the other one. Now, if you could inspect or sort of run in kind of an expect in a way that doesn't just stop when first hits the first error, but keeps on looking for more, then you might be able to get an idea of which of your different options make the most sense. So in this example, imagine fill legal form 1, they didn't include the right attachment, and they're missing a parameter. Fill legal form 2, all they did was ask for the incorrect route. Maybe in the subject line, they said, hey, I'd like to fill legal form 1, but they meant legal form 2. Fill legal form 3 has a gazillion things wrong with it. So, how could we implement that? So again, it's kind of going back to sort of adding some additional kind of effect, injecting some additional effect versions. So because arrows have things like a parallel constructor that make it easy for us to know which things are sort of running in parallel versus sequentially, it makes it easy for us to sort of write some simple logic that says, try to execute your first arrow. If that guy throws an error, you're going to be done. But instead of actually just being done with that first one, try to run the second one too, because maybe you're going to get some list of errors for that and then concatenate it. So the third example essentially does that. Just a simplified example, but you can imagine this guy being generalized. So kind of out of time, but I'll sort of mention a couple of other tricks, some which might be morally suspect, but are things we've been thinking about. One is you can imagine sort of doing even more out of band splicing, right? Aspect J kind of stuff, where you sort of instrument the execution with logging and security. I mean, that's pretty standard like free monad things, but. Imagine you wanted to actually change the structure. So if I had, some pure part of the function and then some effectful part, and I want to just sort of run the first part, kind of test the first part without actually touching the database or actually going out to websites and doing anything that's going to cause any lasting effect. You could use this process to kind of pull out a subset that just does pure, or you could imagine you've got 3 processes in parallel. That's what I've defined, but I just want to run a couple of them, so I kind of resplice, pull apart my arrow and put it back together with fewer parts than what it had previously. The other piece that we've been playing with is, if you've seen this computational semantics book, the idea is that there are sort of ways to equate semantics with kind of predicate logic. Usually you have like a database, a model that describes what's true. You could use these arrows as sort of to drive your model and use that to be able to answer questions about, do I have a feature that deals with PDFs? Do I have a feature that deals with PDFs and talks to the database? And sort of have all that wiring happen without any special case logic. Okay, and with that, I guess that's it. So special thanks to the various Stack Overflow saints who've helped me along the way. LambdaConf 2006 organizing committee, and Holland Hart, my employer. So as I mentioned, we're a very small DevOps team that's inside the law firm. We are growing rapidly, so if there's any people, we're located in Boulder, that are interested in natural language processing, interested in doing Haskell, then we're always looking for good people. So, thanks. Any questions? Yeah, Jimmy.
So I noticed that all your annotations were static.
Yep.
Online. Is it possible to, add like?
Yeah.
Words, words?
Yep. So if you actually look at the implementation, so you go back. This original guy. So this actual annotation type is itself kinded with the same type. So you can, we overwrite from string to be able to just, in the cases where you just need to put some static content, you can do that. But there's other, kind of syntactic sugar that makes it kind of easy if something's showable or whatnot. And we in production we actually use this to kind of to tag all sorts of information that might actually be run in certain circumstances as well. Yeah.
So I noticed that it's only parallel process, two parallel processes, I guess.
Yeah.
What if you want to expand past that?
Then you have 3 parallel processes.
What
Yeah.
do you do? Do you transform it together with another one or nest it or?
Are you saying in the original construction? The
Yeah.
original thing, yeah. So for arrows, you can, you could split the first one and the second one could be a split, and the second could be a split, right? That's how you get sort of in parallelism that way.
Cool. Thank
Does
you.
that make sense? No. Oh, do we have? I guess we're all right, thanks. If anybody has any questions, please.